Hello everyone, Namaste. I am Ramnath who would like to present to you the series on key learnings from chip development, part 6, which is on formal verification, particularly on equivalence checking. This is the continuation of the earlier part 5. Formal verification equivalence checking of combinatorial circuit analyzing methods are discussed in this uh, part. So there are variety of methods exist. Out of that, we will cover the truth table based analysis, binary decision diagram based analysis, combinatorial circuit satisfiability based analysis, and Tseitin transformation based analysis. So Boolean satisfiability or SAT for a given Boolean formula, it checks whether the Boolean formula is satisfiable or not. So, and these SAT solvers actually have emerged as very powerful tools for tackling combinatorial problems. And there are definitely different updates to all these processes because the state space size matter. So the Tseitin transformation takes the combinatorial circuit as input and uses it on Boolean expression and performs De Morgan's and distributive properties to convert it into equisatisfiable Boolean formula. So considering the various updates and all, here I am basically covering the basic concepts related to them. Thanks for learning along with me. Feel free to provide your suggestions. Thank you. We will know more about the formal equivalence checking, which is mainly used to know whether the synthesizable design and the pre-routed netlist are the equivalent, or post-routed netlist and ECO netlist are equivalent. For those kind of situations, this equivalence checking is more often used. Okay, so here again there are two parts to it. One is combinational equivalence checking and sequential equivalence based checking. We will restrict most of the parts to combinational equivalence checking, and we will consider that sequential equivalence checking can be mapped to combinational equivalence checking provided their registers or cut points are having the same registers. Okay, and it is also possible to the tools, even if the internal registers are not same, sequential elements are not same, it is possible to evaluate. However, we will not go too deep into that aspect. So we will restrict our analysis only onto the combinational equivalence checking. Truth tables we can use with the designs we are exploring are very small. So definitely when the design size increases because of the exponential growth of the truth table, it is not possible to uh, do it because it is not practicable. However, it is possible. In the earlier times, this was used. Okay, coming to the binary decision diagrams, so the BDDs, so a specialized data structure designed to support reasoning about the Boolean functions was constructed, and BDDs have become highly popular because of their efficiency and versatility in 1980s. Okay, this was a Reynold from CMU who has written one paper on BDDs have become so popular and so many times it was cited. And it is also possible to write the uh, function in terms of a formula, and then you can also figure out whether those formulas of two different designs are they equivalent or not. And it is also possible to figure out the modules or blocks whether they are taken through the satisfiability solvers, whether they yield the same result. For that we need to know based on the conjunctive normal form or disjunctive normal forms to aid the analysis. So here we will know that, so if for the CNF conjunctive normal form satisfiability, SAT solvers returns an assignment to the variables of proportional formula that satisfies it if such an assignment exists. Okay, and this is possible to do for any Boolean equation. To compare the golden and revised designs for equivalence, so especially here we are talking about the combinational equivalence checking. We need to decompose the design into small pieces for easy handling. Okay, so here we are considering such a small block having the inputs and outputs which are same, or they're based on their, this is basically figured out through multiple methods, and we will come to that. And here you can figure out that there are several internal points. So for example, A 100, 110, C 110, like that. There are multiple points. Between these points, either they can be going to the outputs, and some of them can be tied to an input also. So you can figure out that there are several combinational blocks existing. Okay, in the same way, revised design, this is assuming golden design, revised design also has similar inputs and same cut points. Okay, then we will know that, so this points, you can, since they are part of the registers, you can say that they can be represented as some register flip-flops, and they can be part of either a combinational gates, these elements. So now what will happen is, like, we have to figure out that this is the, based on this we need to write the certain circuit equation for this golden design. And in the same way, for the revised design also, we need to write what should be the design. So here we are picking up the same registers based on the hierarchical name, or based on the known information about the design. So we need to figure out those internal registers even in the revised design based on the inputs, or based on the hierarchy or names or certain knowledge of the system. We need to figure out the same transition points, and then we need to come out with the and we need to compare these two designs. So this design block need to be made into a formula, and that can be any canonical representation, and that one we need to take it through the binary addition diagrams. Okay, this is one method. Then we need to compare these golden design and the current revised design. Here in the revised design also, the cut points are actually same, the numbers are same. So then we will know that whether, when we take it through the same type of inputs through the BDD, in the golden and the revised designs, do they yield same results? Based on that, we will say that this portion of the DUT, is it equivalent or not? So as discussed earlier, a big design is decomposed into small pieces based on the suitable cut points. They need to be verified also that these cut points are equivalent by tracing through the inputs. Once that has been established, assume that there is a decision node A which has two child nodes. Since we are talking about binary, so there will be child low, child high for this node A. Similarly, for this child, there are for this decision node, there are two children. One is child low, another is child high. For representative purposes, easy handling, we will represent the 0 with the dashed lines and thick lines with 1. So the specific equation will be based on these specific inputs. The results are mentioned here. This is done for the same uh, blocks which are part of the golden design, and for the same cut points for the golden revised design also, for that equation need not be exactly same. So for that also the results are figured out. So then the results are compared through the XOR. If the results are equivalent, then we will say that these two blocks found out through binary decision tree for the golden and revised designs are same. However, as mentioned in the earlier slide, like it so happens that even though cut points and these inputs and all those things are almost same, however, there are certain situations where the blocks may not be exactly same. The result binary decision results may not be same. Then we will figure out at the functional level, the parent level, and then we will see whether at parent level of these blocks, including other blocks, is the functionality matching. The Boolean satisfiability problem is to check whether a given Boolean formula is satisfiable or not by assigning appropriate logical values to its variables. So if such an assignment exists, then Boolean formula is said to be satisfiable. In short, it is called SAT. So on the other hand, if no such assignment exists, then the function expressed by the formula is false for all possible variable assignments, and the formula is unsatisfiable, unsat. So this is actually used in many applications in the areas of computer science and theoretical computer science and complexity theory and cryptography and AI. Okay, and in our context, this is very much used in formal verification to find out whether two functions are equivalent or not. In the earlier situation, we have figured out how binary decision diagram could not figure out a function as equivalent or not. That one we will figure out how the Boolean satisfiability solvers will solve. Okay, before that we will take two examples. So in this example, so P equal to A and B bar. Okay, so here this is the representation, and true. So if we apply B A equal to true and B equal to false, then A this will be P becomes true and not false. That means like true and true, that means it is true. Since it is true, this expression P equal to A bar B, AB bar, sorry, AB bar is true. So that means like P is equal to satisfiable for so variables. In the same way, in the current another example, you will observe that consider another expression or formula M, where M equal to C D bar plus C bar D, XOR function. So C and D bar plus or C bar and D, this one. So if you apply for this specific function M, which is an XOR, the values for C and D as true and D also as true, then you will notice that this one becomes true and not true, or not true and true. So if you take this one, the resulting logic value is false. That means it is unsatisfiable for these values. What it means is, so this expression now is unsatisfiable. Hence we will say that this is the functions C and D are equivalent. Okay, now we will go back to the binary decision diagram wherein we have discussed like F2 and G2, some intermediate logic of the design are coming out to be non-equivalent based on the BDD, binary decision diagram. Then we will figure out what will be the based on the satisfiability solvers, whether function F and G, whether they are equivalent. So when we try to find out, put these equations on this one, and then we will find out the XR of F and G, then if that one comes out to be unsatisfiable, then we can say F and G are equivalent, like this. Okay, then we will say F2 and G2 are actually producing false negative. That means like based on BDD, this appears to be non-equivalent, but when you take the entire circuit of F, entire circuit of G consisting of F2 and G2 respectively, then they are equivalent, then this seems to be, then this can be considered as false negative. Briefly digressing, God is giving so many items to each of us. What will happen at his end if he performs this SAT check on us? We will know some basics of Tseitin transformation. So for that we need to know how the disjunctive normal form and the conjunctive normal form, these things mean. Okay, these are some of the basics and which will be used more often. So CNF stands for conjunctive normal form. So here it has the conjunction of clauses. Okay, so if you see here, so this is the product of sums. That means like product of A1, A2 literals, B1, B2 literals, C1, C2 literals, their product and their how those literals are present means they are based on sums. So this is called sum and these are the products. So this is product of sums and this one is sum of products. Okay, and here before we go what these symbols mean, we can say that these symbols mean actually inverted V stands for and, V stands for or. So this means A1 plus A2 plus A3 like that, and B1 plus B2 plus B3 and Bm like that. So and this symbol means not. Okay, so there are clauses and these conjunction of clauses. So here these are all different literals and any Boolean function can be represented in either CNF or DNF. For all our further analysis, we will be basing our analysis based on CNF. Just for analysis, we are taking one CNF formula where it has three variables x1, x2, x3. Here what it means is x1 plus x2, okay, plus x3 and x1 bar here plus x2 and x2 bar plus x3. So and how to solve it through SAT solvers is mentioned here. For reference it is provided. Since the golden and revised designs which the formal tool will handle contain the gates, primitive gates, either in inverter, NAND, NOR or AND gates or any such gate, how they will be interpreted by this Tseitin encoding will be analyzed in the coming slides. So here each logic gate is expressed in a CNF form. We wanted to represent one equation based on inputs A and B. So this is slightly different. So in Tseitin encoding, so where we not only take inputs, we'll also take output information, and we will represent both input and output in terms of CNF to represent how the gate will respond. So when that expression, when it is evaluated and satisfaction is ensured, then we can say that the inputs and outputs are handled correctly, and we are getting the correct operation of the gate. Okay, so here to do that one, we will find out the expression of W involving both input and output. So if you see here, when A equal to 0, output B, okay, output B equal to 1. So we will say that expression W is 1 here. That means like that sub expression will become 1. And when A equal to 1, B equal to 0, at that time also the sub expression should be true. So, and when A equal to 0, B equal to 0 is invalid or forbidden pattern. So we will not consider this. Similarly, when A equal to 1, B equal to 1 is forbidden pattern. So W of this function of this inverter gate is A, B bar here represented, and to represent this one, A bar plus A bar B, that is this one. Okay, so this is the R of it. So W represents A B bar plus A bar B, this function. Now this is not in CNF form, so we wanted to bring this into CNF. So we will figure out how to do that. So there are different methods. So this method, since we know about how to using De Morgan's laws, how we can compute. So I used De Morgan's laws and then figured out the canonical conjunctive natural form. Okay, so if you see here, W is same as this one here, but I put 2 bars. Okay, so that this one and this one are exactly same. Now applying the De Morgan's law, so here we know that not of A or B is equal to not A and not B. Not of A and B equal to not A or not B. So you will observe that applying 1 bar here, what will happen is this became A bar and became R, B bar became B using this equation. Okay, and similarly this R became and then this part became A and became R, and then this became B bar. So using this equation. So now we have to resolve this one. Before we resolving it, let us expand it. Okay, so we multiply this term with this one. So then we get A bar and B bar plus A, B. Okay, now we apply the bar. Okay, so when we apply again the De Morgan's law, then we will know that this means, okay, here we will observe that A plus B and A bar plus B bar. So this is the now equation. So this W and here this W both are equivalent. Okay, so we just represented this expression in CNF form. So these are the two sub-expressions. One sub-expression involving both input and output, another sub-expression involving both input and output. So these individually, this sub-expression should be satisfied to true. This sub-expression should be satisfied. So true. So when both these sub-expressions are true, then we will say that this expression W is true, satisfied. So this representation is in this fashion. Okay, this is OR gate, A plus B and A bar plus B bar AND. Okay, and how this W will come in a truth table based thing is, so when A and B are false and true, A plus B is true. Okay, and when A and B are false and true, A bar plus B bar is true. Similarly, when A is true, B is false, then A plus B is true and A bar plus B bar is true. So we will, in these, when any of these two patterns happen, then we will get that these two sub-expressions, both for input and output, then the W will be true. However, if we apply this pattern, this sub-expression becomes false. This sub-expression became true, but true and false becomes false. So this sub-expression W will become false if the inputs are false and output is also false. That means like the gate is no longer an inverter. Probably it is more like it is a buffer. Okay, so that is how we'll say that this is the satisfiable T is ensured for an inverter. So we will keep formality 2 will keep the gate and this sub-expressions. So now this whole thing, how it maps, everything is known as part of a library kind of thing. So now when this whole thing is processed, it will quickly know, yeah, for this gate this need to be done, so this expression need to be used. We will come in the following sections. Let us inspect how AND gate will be brought into Tseitin transformation. Okay, that means like how we will bring the inputs and outputs sub-expressions of AND gate in CNF form. Okay, so if you see here, AB are the inputs, C is the output. Okay, so here input and output, and C will take 0 or 1 and AB can take all these 4 values. So as discussed earlier, the forbidden patterns are represented by a red line. So here when 0 0 AB, C becoming 1 is impossible. So the expression W will not take this value. In the same way, when 0 1, this value is ruled out. Even for this value is ruled out. When A B equal to 1 1, C cannot take 0. This is also mentioned. These are all forbidden patterns, possibilities or logic states. So, and in all other conditions, so W will become 1. That means like when AB equal to 0 0, C can take 0. So for that expression, it evaluates to W becomes 1. Now we are representing, as I mentioned earlier, the inputs and outputs of W in n expressions. Yeah, some multiple of expressions, sub-expressions. So this can be written as W equal to, so if you take this one, so we should take these two to get the minimized information. So just like Karnaugh map, I am evaluating this one becomes, so this B becomes redundant. So this is A bar, and here these two C bar. That one is this. Similarly, when we are considering this one and this one, so that means like here these two and these two. That means like A becoming eliminated. So this becomes B bar by taking these two, and these two means C bar. That is this one. Okay. And coming to this one, this is alone. You cannot merge with anything. So here it is AB. Okay. AB 1 1, and then C is also 1. So this is becoming uh, so this is becoming ABC. So this is the expression of W. So here, if you observe, W is consisting of inputs and outputs. So this one. So this expression, now we need to bring it into CNF form. So how we will bring is like we'll make a small modifications. So here for in these two sub expressions, yeah, C bar is common, so we've taken it, and then we are now bringing it into CNF form. So we will do 2 bars to prevent the data manipulation, and now this becomes A plus A and B because of this 1 bar application using De Morgan's law, and this becomes and this is plus C, and here for this one plus, and then this becomes A bar plus B bar plus C bar. Now again we will be applying De Morgan's after expansion. We will get here A bar plus B bar plus C, and A plus C bar and A B plus C bar. So this equation is in CNF form. It has 3 sub-expressions. All need to be evaluated to true. Then only W is satisfiable. In each one should become true. Okay. So this equation is this one, and this one are same. That is, this equation is this whole thing. And if you want to represent it in truth table, that is this one. So each sub-expression is represented here, and they are evaluated. In all these conditions, whatever are considered here, I am representing it here. In all these things, the sub-expressions need to be evaluated to true. Whatever invalid conditions, they will become one of that at least becomes 0, false. So the entire for these invalid situations, W will become false, unsatisfiable. So now if you read, each logic gate expression is represented in CNF form, this one, okay, where the satisfaction of each sub expression enforces the proper operation of a single gate, in this case AND gate. So these are the sub expressions of AND gate. The satisfaction of the entire expression thus enforces that the entire gate is operating properly. So not only one sub expression to be true, all the sub expressions should be true. Then only we will say this W is operating, gate is operating properly, because that is when we will say this is satisfiable. Based on the Tseitin encoding, different gates and their valid states and the possible expressions, sub expressions are shown. So you can see here that for inverter, as we have discussed earlier, these are the sub expressions. For AND gates, these three are the sub expressions, and as mentioned, some of the forbidden patterns are shown. Similarly, for the OR gate, NAND gate, these are the forbidden states, different expressions. So there is clearly between AND gate and NAND gate, the sub expressions are different, and these sub expressions will help in analyzing the satisfiability of the gate. Let us apply the Tseitin encoding on a real circuit. Okay, so here the function I contains AND gate, OR gate, and NAND gate. So different SAT formulas based on CNF, conjunctive natural normal form clauses have been mentioned here. So let us apply for this gate. Okay, this gate has an output I, H and G are the inputs. So for this, how this waveform exists, sub expressions exist, in the same way let us rewrite it. Okay, so I bar in this way, here it is C bar, this is the output, and A, so this is H here as the input, and here again this is I bar plus G, here it is C bar plus B, and here it is H bar plus G bar, here again A bar plus B bar, and I, it is C. So this gate, how the CNF clauses exist, in the same way for this example design, the sub expressions have been obtained. Now we will extend how H will be written. Based on that, we will move further down the chain. So this is the same thing even in the earlier circuits design analysis. We have mentioned that in the formal verification, the analysis starts from the output and go towards the primary inputs. That point we are explaining. So now coming to the H, here you have the input A and another input is F. Now look at this one. Okay, so here again H is the output. So here applying the same thing, C bar plus A. Here. So in the same way, H bar plus A, this one. Similarly, the other. Now coming to this one. So let us take the G here. This is the NAND gate. Okay, NAND gate for this one. In the same way, we will apply the relevant items and then we will get these expressions. That is how this expression is, these expressions are obtained, and now we need to evaluate based on the input vectors for all the sub expressions. All these things need to be true, then only we will get I as true, and that becomes then the satisfiable. Let us apply the Tseitin encoding to the following formula. So here phi equal to naught of A plus B bar or of A bar and C. Okay, this is the equation. Okay, so here this is x phi, which is having xy written as x1 plus x2. Okay, so this for this OR equation, we can take the already available formula here. Okay, so here xy, x1, x2 for this OR formula. Whatever is there here, we can directly put it here. So this one is xy, and we are writing a CNF. So this is x1 bar like this, and xy, and here again here x2 bar or x5 or and here x5 bar or x1 bar x2 and here. Now let us analyze the x1 x2 functions independently. Okay, now x1 is composed of x3 naught. Okay, so x1 equal to x3 naught, which you can get it from here. Okay, so x1 is the output and x3 is the input. Okay, so this here it is x1 bar or x3 bar or and x1 and x3 and here. Okay, now we will go to x3 here. So x3 is x4 or a. Okay, x3 is the output, x4 a are the inputs. So again here, based on this formula, again we need to apply for this one. Now similarly for x5 and x2 and c bar. Okay, so if you now the next function is x2. Here x2 equal to x5 and c. Okay, so yeah, so here by using this formula we will again get it like this is x5 bar and x2. Okay, then and the same thing here. So in that way we will basically expand each of the equations based on the specific formulas we already obtained and the corresponding CNF sub-expressions. So when everything is done, now this CNF is evaluated, and for this CNF function phi to be satisfiable, each of these have to be true independently. Then only this whole function will be true. With this approach, we have covered all the methods used in the combinational equivalence checking, and there are several updates to these methods, and we can easily extend for a curious eye. Okay, and there are also two more equations have also been analyzed after the references section, and feel free to go through in case you want to know more on this Tseitin encoding. Okay, so by using any of these methods based on the design complexity, one can figure out whether the two functions used in golden and revised designs, whether they are equivalent or not. Okay, so that's how the formal equivalence checking will happen, and hope you have analyzed and then got more information from this. To prepare the presentation, these are some of the references I have gone through. Feel free to go through at your convenience. Thank you. This is the end of the formal verification presentations which I have collated. Thanks for your time. So even though these examples are self-explanatory, I'll just briefly go through. So here the design formula is phi equal to P plus R and Q R of not P. So here this is the expression, same thing as here. So we will be starting taking this whole thing as for the phi. Okay, and now we will know that this x5 contains x2 and x3. x2 will again contain x1 and R. x3 will contain p bar. Like that, if we do this whole thing, will be evaluated. One item we can do, So here you will observe that x5 is this one. Then the next one is x2 bar, because now when we are evaluating between x2 and x3, this is an OR gate. Okay, so whatever exists here is x2 OR of x3. Okay, so then we will get this Boolean sub-expressions. So for that you need to see this equation. Okay, how it is written here, in the same way it is put here. So here it is x equal to 5 plus I. Now here for this equation x2 plus x3, this is written in exactly same way as this one. Okay. Similarly for other expressions. That is how we need to evaluate each of these expressions. If you see how Tseitin encoding application applies to phi1 XOR phi2. Okay, so phi1 expression is so, phi2 expression is this. So how, based on this, we will say whether phi equal to phi1 XOR phi2 is satisfiable or not. So we will again take here in the same fashion. So phi1 we will substitute here. Again this one we will put the values here. So phi1, this XOR we have expanded. So this is the XOR expansion. Now we have substituted phi1 and phi2. Now we have evaluated each item based on these expressions. Okay, so we have cut it into multiple pieces, how it should be based on the associated symbols for OR and AND gate and NOT gate, and then we have used these already existing expressions which we have evaluated based on de Morgan's law and other laws. Then we are just combining all of them. So then if we evaluate all of this, then we need to ensure that it is coming out to be either satisfiable or not. So that is how the Tseitin transformations will be taken through based on different waveform expressions. We will be making them into CNF, and then we will be evaluating based on the input vectors. Okay, so again, don't get taken away when we are mentioning input vectors. It becomes a dynamic simulation. No, it will not. So here it is. Basically, we will be using the propagated values we will be evaluating, and this is no way related to dynamic simulation.